Hi everyone, thank you for joining us today for our third talk of our ML webinar series. And today we'll be talking about productionizing machine learning models using Google Cloud Services, a multi-service Dockerized approach. And this webinar series is brought to you by DoiT International and Google Cloud. As I mentioned, this is the third talk in a four-part webinar series. Our first talk on ML without programming and our second talk, Upgrade Your ML Model with AutoML, are both available on demand, and we will share those links with you after this webinar. And join us obviously for the first talk in our series where we'll look at what you do next once you've put your model in live production. Today's agenda, we will be looking at a little bit of an intro to DoiT International, and then even one of our speakers will be looking at an approach for productionizing ML, and Christos from Google Cloud will be talking about automating E2E ML workflow productionization using MLOps. And at the end, we will have some time for Q&A, so please do post your questions in the Q&A section of our webinar, and we will get to them at the end. So I will pass it on to our presenters to talk a little bit about themselves. So Christos, over to you to talk a little bit about yourself.
Thank you, Santi. So my name is Christos Aniftos. I'm a machine learning specialist working at Google Cloud. I've been at Google for over 2 years now, and my role is to help Google Cloud users, our customers, to understand and best utilize the machine learning capabilities we offer. And back to you, Eben.
Hi, my name is Eben de Tooy. My current role is data science principal at DoiT International. At DoiT, I play a few roles in terms of data analysis, model building, deployment to production of our machine learning models, and generally to help DoiT deliver pipelines for machine learning into the cloud management platform that we have today. So I'm going to start off our webinar, and this question: are you ready to navigate the cloud with DoiT as co-pilot by your side? DoiT is a premium partner of Google Cloud, and today we have a 5-year, $1.5 billion agreement with Google Cloud to facilitate that partnership and to show the commitment that we have to our customers, and to encourage them to use Google Cloud and DoiT's cloud reliability engineering services to achieve the best outcomes for your business. So we are happy to announce that, and to talk a little bit about DoiT. We have a simple approach, and it's proven, and customers trust us. We have a consulting part of the business with dedicated senior cloud architects, reliability engineers that work with customers on their specific needs, answer their questions, facilitate them when there's problems, and really to help them through some difficult times, perhaps, when the cloud isn't working as they expect, or configuration issues, or any kind of issues that they might encounter, and to share supports that with a platform that is provided free of charge, really, to customers, that really help them to understand their cloud costs much better. So we have what is called Cloud Management Platform, CMP, and as the slide shows, it's like a Swiss Army knife. Inside there, you see your costs consolidated. You get a feel for which direction costs are going for different services. We have an anomaly detection system. It's something I've been involved in quite extensively. Analytics for understanding comparisons between multiple months, and governance and productivity software that help you BigQuery better, understand the cost of that, and also generally help your team to be more productive. So there's no catch to this. All customers of DoiT receive this platform at zero cost, no commitment on their side. Happiness is definitely our top priority at DoiT for our Google Cloud customers, with over 96% customer satisfaction. So let's kick off this episode of the webinar series by talking about manual productionization of ML models. So just to give a slight background of the structure, a lot of companies have got some fashion of productionization for their models today. And what Google offers today is a full end-to-end solution for doing that. So this particular episode will first talk about the manual way of doing it. There's many bespoke ways to use Google Cloud services to put together some form of productionization that works for you. But the next generation, the end-to-end, the full process, which is kind of the gold standard that Google is proposing today, is the next section of this episode. So it's got this natural progression from manual to end-to-end, fully automated. So I'm going to talk to you about the manual side of things. So an ML use case that is very typical today and very useful for customers to have is to detect billing anomalies. Billing in the cloud is complicated. There are many services, each with their own distribution of costs across a month or even a day, even hours sometimes, because multiple users launch and employ these services on a day-to-day basis. Now, sometimes when you launch a service, even though it's clearly documented what the services cost, this cost might be unintended. It might be that the user didn't realize that they are launching a particular service, or that they didn't plan for it. There could be a multitude of reasons why people do this. It is actually fantastic to have a system that is your catch net for that. A system that would inform business stakeholders of any charges that follow that. And if those charges are then out of normal, which is a bit subjective sometimes for businesses, but let's say out of normal is unexpected in general for a business. Those patterns would be key to prevent any further costs from being incurred. So I would like to talk about the core principles of anomaly detection, because I feel it's important to understand a little bit about the system you are going to try and build or the problem you are going to try and solve before you dive into productionizing it. So the thing about anomaly detection is that, as I said, these events are unexpected, and that is in opposition to the usual average behavior that you would get from any system, really. In our case, billing events that are normal billing, and then suddenly you get something that's unusual. But this has got a particular context. And the context of the departure from the usual average behavior is sometimes acceptable. Sometimes a business is okay with getting $1,000 bill for BigQuery if they are used to, for example, a $200 bill weekly. Sometimes that is okay. It could be that somebody was running a big job, and in that context, that job might be once in a while, but still acceptable. So when you're a data scientist and you are trying to build a system, the first port of call is usually the historical data. Then you go and analyze trending, you analyze seasonality, you build distributions, you try and understand what does that look like. But when you use only that, what happens is a business will tell you, no, but this is normal behavior. even if you could say that it's an outlying or a departure, like on the slide, a departure from usual average behavior. Something like this on the right here, where you see in the shaded area, something that was usual behavior, and then suddenly a massive spike. And the only way that you could really know if that spike is truly an anomaly is to also take the business context into account. Now, I would almost say that the 80% case where you use only the historical data is sometimes good enough if you start out with your system and you put your, I would say, first version in place. But very shortly thereafter, once customers start getting these anomalies, you will start to hit business rules and tolerances. So an example again is a question, like if you have a $10 spent on a single BigQuery query, for some businesses, that's very price sensitive and usually have very small data, that could be quite a lot. You know, a small startup company could have a $10 query and complain about this to the person that made that query, whereas a large corporate business would not even think about that twice. So going on from there, now our minds are framed in what is really the context of a departure from average behavior. You have to make some decision with the historical data. How do you really do that? There's a couple of ways to do that. So what we are looking at on the screen here is the typical normal distribution of data. And you can decide if an average billing event falls beyond this line, which is 3 standard deviations away from the average. You can decide that this is a tolerance that you would like to flag on, and then decide, okay, that's going to be my first threshold. Now, you can also see the block down here, which says seasonal billing, which a business is accustomed to, aren't seen as anomalies. And this is a challenge, which I also told you about in the previous slide. So this decision on what is really an anomaly is what it comes down to. The system at DoiT has got 2 layers. The first layer is what we say a prediction of the cost. So the premise on which this is built is that you have a system that could predict what that average behavior should look like. And then if you predicted something, you then decide with the predicted average, the value that you really got from the billing, are those 2 comparable? Or did you predict, is the prediction way less than the actual cost that you got? And then in the second layer, you then classify that level. You decide, is it a critical alert? Is it only information? Or is it an early warning that you can build a system on top of? This is the principle that we used at DoiT to deliver, or the architecture of the system. Now, the prediction of the expected cost, let me go to the next, is using this architecture. I can quickly explain this architecture. We are, as you might have seen in the previous webinar episode, using AutoML, which is over here, to predict this average cost for a particular service broken down per customer billing project, specific usage time, and the specific service, which might be BigQuery or Cloud Run or Compute Engine, or all of the multitude of services that Google Cloud has. How we use the system is we have got Cloud PubSub, and Cloud PubSub is what we can call the messenger. It's the messenger between a couple of cloud servers that we are running in Cloud Run. 2 of them, the ETL server and the layer 2 section, which is the classifier. So what essentially happens here is we've got a bunch of AutoML models, which are currently not running in AutoML itself, but we decided to Dockerize them and run them individually in Google Cloud Run. So today, we have about 5 models for predicting costs sitting in Cloud Run. And the output of those models are also stored separately into BigQuery for further analysis. This whole system kicks off with Cloud Scheduler, which pops up a message to a topic for our billing alerts. And then what happens is a message is then forwarded to the ETL server, which is then routing it to the right place. So this message could be a decision to aggregate historical data. It could be a message to build features. By the way, we are building features using BigQuery directly, which is recommended and very useful. Or it could be a message to filter some features, or it could be a message to say, we have now built up a set of features for a particular billing event, and then that is forwarded to the level 2 classifier. This part down here, performing feature engineering, this is the process where your data scientists are involved, deciding which features are the ones that should be included and which ones shouldn't be. And then you could train an AutoML model, which you might have seen in the previous webinar episode, and include it into the system. So again, this is our first layer that really decides what is the average cost going to be. The second layer is the classifier. So when you productionize this, the way that we've done it, we have a classifier server running in Cloud Run. And this classifier server receives a prediction payload, which is a set of features that have been built, all the predictions, all packaged nicely, and this payload arrives then at the classifier server, which then makes the decision how serious is this deviation or not from the average behavior that it is seeing from our predictions. As output of this, of course, it's only useful if you can get some kind of alert on it and analyze it. So we have BigQuery for analysis of the accuracy of the alerts. We notify both ourselves and our customers on Slack, get their feedback also, and we store the information also in Cloud Firestore because our cloud management platform is driven by Firestore. So we had layer 1 doing the prediction of cost, and we had layer 2 doing the classification of an alert where we see unusual deviation from the average prediction. So let's talk a little bit about the microservices-based manual production deployment of the ETL server. The ETL server has got is a Python-based application running in Cloud Run, and it's got these 2 main sections. It's both a router and a services provider. So the router, as I said, gets messages from PubSub and then decides to clean, predict, extract features, store them, or send along to the second layer. Once this routing is done, it employs a couple of services which we have coded into the application. Obviously, BigQuery, which is doing a lot of the hard work of feature extraction. It's got the Firestore client, PubSub client, and Cloud Storage client, which we are also using to bulk store all the predictions that we make. So now the question, this whole architecture, how do you do it? How do you deploy it to production? It's a manual process managed by a team. First of all, models. models are Dockerized. There are AutoML models, which in AutoML you can export in TensorFlow format, and then we Dockerize them in Cloud Run. That's for models. The ETL server, Dockerized Python application. The classifier server, a Dockerized Python application as well in Cloud Run. Then we have this message routing between the models, the ETL, and the classifier using PubSub. And importantly, the configuration for the above is stored in Firestore, so these applications can read them at runtime. So, for example, if the ETL server is starting up, how does it know when it receives a message which models or endpoints to ask for predictions? So in Cloud Firestore, we store the different endpoints and the different model configurations. And when it's time for prediction, all the configuration is read quickly from Firestore, and it's decided which models are included into prediction or not. So we are talking about having an ensemble of models with the configuration in Firestore. And the question would be then, what if you want to add a model? This is really not a problem. For us, what we did is we trained a new model in AutoML. We exported this and we Dockerized this and put it into Cloud Run and simply updated the Firestore configuration to say what is the new endpoint of the model. And then this configuration is picked up at runtime by our ETL server application right here. So really, even from a manual implementation point of view, it's easy to do, and yeah, a simple configuration. In the last section of my part of the presentation, I'm just going to lift the veil a little bit on this idea of having multiple models in production. Today, using an ensemble of models for predictions is really a great idea, because it could be that some models are better at detecting deviations or predicting costs than others. And using the strengths of all of these models together is a good idea to deliver more accurate predictions. So this is the way that we approached using an ensemble. Today we have about five of those models for cost anomalies. And the way we've done it is we first decided we need to know if the accuracy of models are deteriorating. So the principle is that if a model is deteriorated enough, we don't include it in the final output. But if it's still acceptable, we give it certain credit or a certain confidence level. But that confidence level is based on the errors compared to the actual prediction. So what we do is we have the root mean square error, and we calculate that for a single model over two sliding windows, basically 2 months back and 1 month back. Z-score, which is an indication of how far away from the average a value is for a distribution, is then calculated for the errors between these two windows. And if we see that the Z-score is drifting away, we give less credit to a model. So we just call it weights. And these weights are stored in Firestore and loaded at runtime. A quick explanation. So as I said, we have the Z-score of this population root mean square error comparing two rolling time windows. This is 2 months ago up until and not including the last day of 1 month ago, and then 1 month ago until today. So what then happens is if we detect that the Z-score deviation between these two windows, average error, is drifting away, we give less credit to a model. And it's translated, this drifting is translated into weights. So let's say no drift would then be 100% inclusiveness of the value that we are getting. And you could also have 1% inclusiveness, which is the worst kind of confidence we have in a model. So lastly, of point number 4 says that the less accurate a model, the less influence it will have on the final output. This is what I try to say with the final prediction. Then we have a z statistic of 0 would say between 0 and 2 would say we have confidence of 100% to about 30% in the prediction. From a value of 2 to 2.5, we have 30% to 10% weight to that output, and z-stat of 2.5 to 3 would have almost no confidence or weight in this final output value. Essentially, above 3, we just give 1% weight, where the final prediction of all of these models we have in production is then a weighted mean of any amount of models predictions, this n models predictions. That is the productionization of an ensemble of models using Google Cloud in the manual way. And our pub/sub routing could then periodically trigger the updating of these weights to make sure, because it's a rolling window, we must trigger it every once in a while, let's say every week, to recalculate the weights. So lastly, before I hand over to Christos, we are going from manual to auto now. And definitely there are some gaps to be filled. Nowhere did I mention continuous integration, because this is a manual system, or even continuous deployment. We deploy these things by hand. We have to retrain models when we see they are drifting. And it could also be that we need to auto retrain them. And this is a gap that we have. Another important thing is that customers give us feedback on their business rules, which is then for us labeled data. And this labeled data needs to be included in a feedback loop. So we would say we don't make the same mistake twice. And then lastly, we also need to fill a gap where models and weights and all these ML artifacts need to be stored and version controlled properly. So I would say the answer to that is MLOps with Google Cloud. And Christos will tell you in more detail what that is all about.
Thank you, Ivan. And thank you everyone for joining this session today. So today I will be sharing some of the research that my colleague Khalid Salama put together and produced in the area of MLOps. So let's get started. So you might be familiar with this slide. This is something that we use very often when we talk about MLOps. And of course, there is a research paper, if you want more details, called The Hidden Technical Debt in Machine Learning System. So as this title suggests, when we're thinking of machine learning end-to-end systems, there are more things to consider than just the box in the middle. When we experiment with machine learning, as data scientists, we mostly care about solving the problem that is presented to us, and of course the challenge that we have in our plates. So what we do is we ingest data, we experiment, we iterate until we have a machine learning model that is accurate enough to say that mission accomplished, we solve this challenge. However, this is only a fraction of the workload that is required in order to take this model and move it into production. So I like to think of this as the 80-20 rule, where we spend 20% of our time creating a machine learning model, and then we spend 80% of the time try to correctly productionize this model. So the reality looks like this. Productionization of machine learning solution is a complex thing. One of the reasons of that is because it's unlike computer software codes, data around our models are very rarely static. Usually data evolve, and that creates things like there's no bug into my machine learning code, but the machine learning model doesn't really perform as it used to be because the environment, the data around that changed. So there are many things that we need to consider in order to build a production-ready machine learning platform. And these things are, how do we collect and explore our training data? How do we train our models with not hundreds, but billions of records? I mean, how do we deal with such big scale and volume of data? How do we engineer features at that scale as well? And how do we avoid having the training serving skew? Meaning, how do I engineer features during testing and in development? How do I keep the same engineering process when I serve in production and when I run predictions? How do I serve and monitor the models, making sure that they are up and running and healthy? And the most important is, how do I create an end-to-end machine learning pipeline that is automated? So how do I automate the life cycle so that I can keep retraining and pushing my models into production over and over again? So let's understand how some teams are operating today. And this is something that I have seen many times working with customers. So we have an interesting machine learning problem, and data scientists, they jump into this problem. They pull data from a local data storage that might be either from CSV files or from a local database or a database on-prem or on the cloud, and they start doing some data analysis. So this is when they start getting a feeling of the data, the trends, and so on. Once they better understand the data, then they need to do a couple of steps, which are usually manual, to prepare the data for the model. So they take the data, they do feature engineering, they clean the data, and then they push the data into an algorithm so that they start the training. So they train a machine learning model, and then they evaluate to verify that the model is performing well. And this process is, it happens many, many times because, we evaluate the model. If we don't like the results, we evaluate the model again, and we iterate again and again. Once we have a model that we like, then we take that model, we consider that the final model, the one that we should put into production. And as data scientists, we say, okay, our job here is done. We pass this model to the IT department, to the data engineers, that they should take this and productionize it. So what the engineering team is doing, it takes the model from the data science team, probably from a storage, let's say, for example, Google Cloud Storage. They take that model and they deploy the model in production. And what we notice here is there is a lot of back and forth trying to understand how the model should be served, who is the consumer of the model, what pre-processing steps should happen, and therefore there is a back and forth between the data science team and the engineering team in order to figure out the right way of productionizing this. Right, so the problem with this approach is that it will not scale very well. This approach might be okay for dealing with few models that they don't update very frequently. So maybe it's something that you update once every 6 months. But once you start having a lot of models, a large number of models, and that those models require like training every day or every week, then things start getting very complicated. So how do you really maintain that? Data scientist is a hard to find resource, and you don't want to use your fleet of data scientists to retrain models again and again. This is a very time-consuming process. Of course, as I described, this is a manual process, so you have to do it again and again. It's time-consuming. It's not a reusable asset, so you need to retrain your models from scratch almost from scratch every single time. And when you do this manual approach, it's very likely that you'll make mistakes, bugs and errors. And of course, as I repeated, it's not a nice thing to have. It's not very manageable. So where are we going? Where is this machine learning practice headed? And of course, this is what we advise our customers to start using, is what we call MLOps, but I will help you understand the process of MLOps. Right, so similar to what we did before, we have the data analysis. We get data and we explore from a specific data set. But instead of just taking the data and building our code into maybe a notebook and produce a machine learning model, what we need to produce is assets that themselves will create the model. So what I mean by that is we need to create the code that orchestrates a machine learning pipeline. So that orchestrate box here is the code that will take care of data ingestion, cleaning data, doing feature engineering, training a model, comparing the model, evaluating the model, of course, and pushing that model into production. And remember, we are not doing that step, so we don't train and produce a model and push into production. We just create the code that does that for us. So this is what we call orchestrate. So here is when we put together our machine learning pipeline. For that, we will need configuration, so where this pipeline might run, all the assets responsible for the execution of this pipeline. Of course, what we need is we need to iterate and being able to run this again and again. So this source code that is produced will be stored into a source repository, something like a Git repository. Then what this will trigger once we save our source code into the repository, it will trigger automatically our own CI/CD pipeline that will take that code and do the following steps. It will take our source code, and based on that code, because remember that code is a definition of the steps we want to run, it will take the code and build components and the pipeline. So whereas the code just defines that pipeline, now we will compile the pipeline. And if we think of Kubeflow pipelines, that will be a zip file of our definition of the pipeline. We will build components. So a component might be our feature engineering component, might be the training job component, and these might be containerized steps or components in the form of containers or in other format. We will also automate tests. Those might will be unit tests and integration tests to make sure that our source code, for example, the code that does the feature engineering step, it's valid. So for example, if you engineer a feature calculating the age of an individual based on their date of birth, then you need to validate that the calculation of the age is correct. For that, we deploy some unit tests and we run them to make sure that everything is green, everything passes. Then the artifacts we create, which is basically the components we build, maybe containers and the pipeline itself, we store them into an artifact storage. And of course, we deploy to the target environment. What we deploy here, again, it's the compilation of our pipeline. And then what we do is from the artifact store, we pull all the artifacts, the pipeline and the components we built. And with some fresh training data, we start running our pipeline, which is responsible to extract data from the source validate the data, prepare the data, push the data into the model, and do the model training step, evaluate the model, and then validate, make sure that the model is valid to go into production. The model is better than previous model I've seen. And of course, when we're ready, we want to push that model into a model registry. So this is where we hold all our models, the models that we trained using this pipeline. What you see here highlighted in red is, of course, some safeguards for creating this new model. Remember, the end goal is to automate our end-to-end pipeline. So what we want to make sure is that, when we automate things and therefore we produce assets automatically, and then we push these assets into production, we need to ensure that if something goes wrong, we won't productionize this model. So data validation checks that there is no big change in the data that the model previously saw, or your code or your training job previously saw, compared to the data that we are training today. So if I put this into context, imagine that we train a machine learning model every week. So we know the data we trained last week and the week before, and we know the distributions and standard deviations of this data. So we know how the data looked like. So imagine that today I'm trying to train again, and suddenly I have data that they look way different than the data I had last week. So maybe the mean change, or maybe there is a feature that is missing. What I need to do then is to stop the training and notify the data scientists by saying, hey, there's a change in the data, and therefore I need manual intervention. The model validation step, so the second highlighted box here in red, is when I validate that this model is good to go into production. Here I care about the accuracy of the model, perhaps how the model performs in different demographics of the data, if this model is better than a previous model I had in production. Right, and a few things that can make this a whole better experience is the use of metadata store. Super important to track all the executions, all the experiments, and all the jobs that are running in the system. So the metadata store allows you to be able to understand, for example, what data were used for a specific job. What data were used for the model that is now in production, or for every version of a model that you created in the past, saved into the model registry. It helps you know what were the performance metrics of those models, who trained the models, what code was used, what versions of container images were used to train the model or to do feature engineering. Therefore, if you have any questions about who trained the model, how, when, what happened, what you need to do is look inside a metadata store and get the answers that you look for. Lastly, the feature store. So the feature store allows you to standardize and how you produce features. It allows you to share features with other colleagues inside the organization, and ensure that the way you are generating features, it's exactly the same way as other people consume the same features. So let's say that you're doing a calculation, a complicated feature engineering to find out, if we think of recommendation engine, to find out how people are kind of clustered in specific groups. You don't want other people in your organization, when they have the same task in hand, to create clusters of people for a recommender engine, to create these clusters in different ways. You need to come together and agree and make sure that the clusters are created the same way. So using a feature store, others can go and search for features that someone authored, someone created, and then use that instead of creating their own code that might be different than the code that other parts of the business is using. Feature store is also important when you serve the models to make sure that the same way you engineer the features to train the model, it's the same as the model that, sorry, the engineering of those features is the same when you use them in production. Yeah, those are super important when you want to have a production ready system. Right, so similar to the concepts we've seen before, after we train the model, we need to productionize the model. Here we pull the model for the model registry, and we use, let me just use it. So we pull the model for the model registry, we pull code from the source repository. So this is the productionization code. So this might be a Flask application that wraps around the model. It might be a TF serving application or something else, of whatever you like and whatever you're using. The idea here is that we take the wrapper, we take the model, and we create a service. We build that service. We run tests to make sure that the service serves. If it's a REST API, we need to run tests to see that if we submit a request payload, we get back a response. And lastly, we deploy this service into our target environment. Once we do that, then we have a service that is ready to accept traffic. So we send live data to that endpoint. So we do predictions. We might use explainability. I won't discuss explainability today, but you can have a look into our explainability service on GCP to find out more. We evaluate the models by logging all the data, all the traffic to this API, and we monitor, make sure that the models are up, running, and healthy, and that their performance doesn't degrade over time. And of course, everything that we do here, we log it so that we are able to debug and answer questions. Right, so here we have a view on how you can do MLOps on GCP. And you might notice that before we were just talking about concepts. I didn't mention a single product because I wanted you to understand what MLOps is and how you can implement MLOps in general. If you want to implement MLOps on GCP, this is one approach that you can take. Initially, what we care is, we need an environment to do data exploration and analysis, understand our data, and of course, create our assets. And for that, we use AI platform notebooks, which allows you to pull data from a data storage, experiment, and develop there. AI platform notebooks, it will be a familiar product to the majority of the data scientists because it's a product that is based on Jupyter Lab and Jupyter Notebooks. And the difference is that this product is on steroids when it comes to GCP because it integrates with other GCP products very well, and we make the experience easy for the data scientists to pull data and analyze them in those notebooks. Of course, they're scalable in terms of you can select a notebook with the required amount of RAM, memory and computational power, but also it allows you to attach different GPUs if you want to utilize those. You can use TPUs from notebooks as well. And one of the benefits is, as I said, integrates very well with other services on GCP. For example, BigQuery. So BigQuery is our data warehouse. So this is where you would store all your company's information because then you can request and retrieve this information very, very fast in a matter of only a few seconds. You can analyze petabytes of data. So this is a good location of having your raw data. So the idea is you pull your raw data, you experiment, and inside your notebooks, you can create code and configuration. That code code is getting pushed into a code repository. On GCP, we offer cloud source repository. If you have to use other repositories like GitHub, we have integration with that. So if you prefer using GitHub because that's what the company is using, then you're very welcome to use that. Then you can, of course, based on your commits on your cloud, on your code repository, you can trigger a cloud build. Cloud build is a service that takes a definition of a build, and this definition is essentially you define that, it's a YAML file, and you explain or you define what assets you want to build or when you push your code into your code repository. So those assets might be compiling your pipeline, creating containers, for example, or any other assets, configurations that you want to package and put into cloud storage and so on. So if we think of, let's say that I'm building a Kubeflow pipelines, then you're very likely going to have steps that are containerized. So you will push these steps, compile them, and build the containers, and push them into the container registry. And we call those pipeline steps as pipeline components. And the pipeline itself, which is a zip YAML file, you can store that into cloud storage. So this essentially is the pipeline definition. This is what Kubeflow might take as an input in order to create a pipeline graph and execute that pipeline. And of course, what you want to do when you execute that pipeline, you can run the pipeline on AI Platform Pipelines, which is a Kubeflow Pipelines instance that is deployed on GKE. And when you run your pipeline, you provide inputs. So when you train your machine learning model, you say, this is the location of my training data. This is the parameters I want to use for this training job. Might be parameters for the model, like if it's a neural network, how many neurons and layers to use, for example. The pipeline runs, it pulls data from BigQuery, the data warehouse, as we said. The pipeline, of course, it runs perhaps based on a trigger, a scheduler. So you might use Cloud Scheduler here to schedule executions of this pipeline. The pipeline produces assets. So when it runs, it produces assets that, of course, you can host on the model registry. That might be your model. And what you do is, you take that model and you serve it on, using another cloud build. You take that model and you serve it on AI Platform Prediction Service, for example, and then that is ready to accept traffic. You can log the traffic and the predictions that the model is making on another BigQuery table, so that you can then detect if the model is, you use this logging essentially to monitor the performance of the model and see if there's a drift and make sure that the model is performing and behaving well. Your pipeline, of course, can outsource the training job to our training service. So the step that trains the machine learning model could be sent to our GCP training service, AI Platform Training Service, and therefore you outsource the training step as well. So with that, this is what I had to share with you today. This is an example of an architecture. We have a blog, a nice blog that elaborates more on this, and we will be very happy to share the link to that blog later on with all of you. And with that, I think it's time to move to the Q&A section, and back to you, Xanthi.
Thank you both, Christos and Eben, for these wonderful slides and information. I have a couple of questions that have been submitted. So we'll take a couple minutes to answer those. I think I'll start from a couple questions that are related to your section, Christos. So one question was, what service product would you recommend to use for the feature store?
That's a very good question. I think from the open source community, you can get Feast. That's a feature store which is open source that offers real time and batch serving of features. I guess the other approach is to create your own feature store depending on your needs. Few of the important considerations is to decide if you need something super fast in real time, in which case you might look into implementing a feature store using Bigtable storage. If you need features that you want to retrieve in a batch manner and not in real time, then something like BigQuery might be the product that you would like to use to build your features on top. Yeah, but Feast is the open source solution that also Kubeflow ecosystem recommends as well.
Thank you. And another question for the feature store: is the feature store more to do with code or with feature data?
So the feature store is the location where you keep data, and it has to do more for feature serving. So how do you retrieve features from the feature store? How do you make use of those features? But in order to populate the feature store with features, you need the code that goes and engineers those features. So that is the element of of coding, the calculation and preparation of those features. Then you ingest those into the feature store, and then you have them there ready for the data scientists to pull them and use them.
Thank you. I have another question around the architecture that you shared with us, Christos. So the question is, can we use the same architecture in GCP to build a recommender system in real time?
So that is a generic architecture. So yes, you could use the architecture we shared in order to build a recommendation system. It depends, of course, on the details of your implementation, but generic concepts, generally speaking, you could replicate this architecture. You could build your recommender system like that.
Thank you. Loads of good questions to pick from. So let me try to find another one. Right, another one for you, Christos. So an automated E2E pipelines, is the source code produced manually or partly generated by some high-level tools?
So it depends, again, on how you want to build your pipeline. There are different orchestrators where you can select from. The dominant orchestrator for machine learning pipelines is Kubeflow pipelines, or if you're heavy user of TensorFlow, you can pick TFX SDK to orchestrate your pipeline. So the idea is that TFX provides you with an SDK that allows you to orchestrate pipelines. Kubeflow Pipelines has also its own SDK, and you can use that to build your pipelines. You write code, but by using the SDK is way easier, of course. So you can use the SDK, you define your pipeline sequence, then you can compile, and then that gives you the DAG, which you can run in your orchestrator, for example, in Kubeflow pipelines. Some other tools we can use is Composer and Apache Airflow, which is another way to orchestrate processes. It's not very specific to machine learning, but they're more generic orchestrators, but you can still use them to orchestrate your machine learning pipelines.
Right. And again, around the architecture. So I had the question right in front of you. Sorry, in front of me. Sorry about this. I'll move on to another one, which I found. So, how is the rapid experimentation different from exploratory data analysis? Is the building source code for the training pipeline based on exploratory data analysis? Not sure why it's called experimentation. So that was a question that we received.
So what we mean by the exploration step or the exploratory analysis is when we try to understand our data, trying to understand the problem at hand, what is that we're trying to solve. So usually we need to peek into the data, analyze the data, understand the problem, and that is something we can do inside a notebook. It's beyond we're even thinking of kind of running this at scale. Once we are confident and we understand the problem, we understand that, well, this is a recommender system or this is a classification problem, these are the data, we understand all the features, then we want to create a framework that allows for rapid experimentation. What we mean by rapid experimentation is creating a pipeline in a way that it allows us to run it many, many times by selecting different parameters. So that might be parameters for the model, that might be selecting different features, that might be selecting different data overall, or maybe selecting all of our data, which might be billions of data points which we need a distributed system to run. So we go from exploration to experimentation, and we want, when we run experiments, we want to be able to run experiments fast. We want to be able to replicate these experiments. We want to be able to share these experiments, share the components that we use in our experiments with the rest of the team. So experimenting, imagine that you run 20 experiments using an orchestrated pipeline which you created that runs on Kubeflow pipeline. You want to be able to go back and find out which experiment produced the best results, right? So that's why you need to have this framework in place.
Thank you. And then I have a couple more questions. How about running the predictions on Cloud Functions instead of Cloud Run? I don't know if that was a question for you, Eben, or if it was for Christos.
I think that might be for Eben.
Yeah, that's fine. So, I mean, you can run predictions on Cloud Functions. It depends on resources that you need. Cloud Run, you can, today we are using Anthos, which is a backend that is Kubernetes. So we can decide how much memory we need for these models. Sometimes they are quite memory intensive. As an example, one of these 5 models we are using for prediction is about between 10 and 20 gigabyte of memory needed. So I would say it's a better architecture for us to use Cloud Run. But for smaller models, I would say Cloud Functions would be suitable. Yeah.
I'm sorry if I'm not pronouncing this correctly. I think it's KNIME or KNIME framework offer the AI pipeline you presented with GCP.
It's a question for Christos again.
Yeah, so sorry, how do you spell it?
KNIME.
Right. So I had a look into KNIME in the past, and I think that's kind of a lightweight framework to be able to run your pipelines. I'm not sure if you can use it as is to deploy the architecture we shared. I guess we can take this away and maybe get back to you offline on that.
Right. Yeah. So we'll make sure to go back to Stephanie on this. So I think this is a question for you, Eben, because it's related to AutoML, which you showed us at the beginning. When you say AutoML model, what do you mean in this context? Is it a suite of models that you tune online and pick the best one? Or is it a framework you are using to pick the best model quickly?
That's a nice question. So what exactly I mean by AutoML? AutoML is a service by GCP. It's called AutoML tables. And in AutoML tables, you can quickly build models, and the GCP algorithms behind this will produce a model. This is what I mean with AutoML model. Now, what we have are multiple of these trained AutoML models, which is then exported in a package format. Incidentally, it's the TensorFlow format, but this in a way is hidden to the outside user. In essence, we have this code in which the model is now packaged, and that is Dockerized. And then what we have is we've got multiple Dockerized models, and then we apply that algorithm I discussed to select the ensemble output or the final output from these multiple Dockerized models.
Great, thank you. We'll take a couple questions because I know we're over time. So you mentioned the feedback part via Slack. I think this question again is for you, Eben. Is it something like labeling, reporting some alerts as false positives, so the feedback is considered later on?
Yeah, this is a great feature of the DoiT cloud management platform, is that a customer of DoiT using this platform select if they want feedback or not into their into a Slack channel. And what this message looks like is it provides you a link and a graph showing you a particular service, a project in which an anomaly happened. And then it provides you some buttons. One button would you click and it will open the actual report for you, where you can look into the anomaly inside our cloud management platform. But then you can also click on a button that will tell you it's interesting to you or it's not interesting, like a feedback providing us with labeled information. So you could say, this is not great or this is great.
Thank you. And then one final question. Do you provide the solution to your customers as a service? Again, I think this is related to the anomaly detection feature that you showed us, Eben.
Yeah, absolutely. So we provide this to all our customers, and you can use it. It's something you opt in simply by ticking a box and selecting what type of alerting level you would like. If you want a lot of informational alerts or warnings or even critical alerts, you can select what your tolerance level of alerting would be, or for all customers of DoiT.
Thank you both, and thank you to everybody who joined us today. If you have any more questions and any of your questions we didn't get around to, we'll make sure to get back to you over the next couple of days. If you have any more questions, feel free to send us an email. You can very easily get in touch with us on our website, as well as responding back to some of the emails that we'll be sharing with you, the recording and some of the additional information, such as some case studies, the blog that Chris has mentioned, and a link to the book that he also mentioned. So again, thank you very much for your time. And we look forward to seeing you at the next machine learning webinar that we will be hosting. Thank you so much.